The next speaker is Meir, who will be telling us about the KRW Conjecture.
Thanks. The KRW Conjecture is what I believe to be a promising and an exciting approach for proving depth lower bounds. And my main goal in this talk is to draw your interest to this conjecture and invite you to join us in proving it. So I'll focus less on the details of particular results and more on a broad overview of what is known and what are some nice open problems we could work on. More specifically, the talk will have 4 parts. First, in the introduction, I will just tell you what it is all about. Then I'll discuss what is known about this conjecture. Then, just to give you a flavor of what is going on, I'll discuss one proof strategy that has been useful in proving some of those results. And then finally, I'll describe some future directions which I believe are good for proving this result. Let's set up the scene. We are interested in proving depth complexity lower bounds. So given a function f, its depth complexity is the depth of the shallowest circuit that computes f. And here we talk about the Morgan circuits, that is circuits that have AND, OR, and NOT gates. And the depth of a circuit is just the length of the longest path from an input gate to the output gate, and in a sense it measures the running time of a parallel algorithm. Another important convention to keep in mind is that we consider only circuits that have fan in 2. That is, every gate has only 2 incoming wires. Now, one of the major frontiers of circuit complexity and complexity theory in general is to come up with an explicit function f that has a super logarithmic depth complexity. This is also known as the P versus NC1 question, and in a sense it's a question about the relative power of parallel algorithms versus sequential algorithms. So we have this grand question, and now let's ask ourselves, how do we approach it? Well, one approach was suggested by Karchmer-Wigderson in 1991, and they suggested that we should try to understand composition. So I'm now going to define the composition of Boolean functions. This is probably the most important definition of this talk. So if you are thinking you are falling asleep, I suggest you do it on the next slide. So if we have, say we have 2 Boolean functions, f from m bits to n to 1 bit, g from n bits to 1 bit. The composition is a function that takes an m by n Boolean matrix x and performs the following computation on it. First, we know that the rows of the matrix are just strings of length n, so they are a legal input for g. So we compute g on the rows, and now we get a string a, which is a string of length m, so it's a legal input for f. So we compute f on this string, and we get, and the value we get is the output of the composed function. Any question about this definition? Okay, good. So now that we have defined the composition of Boolean functions, a natural question is how does depth complexity behave with respect to this composition operation? And it is not hard to see that the depth complexity of the composed function is at most the sum of the depth complexity of f plus the depth complexity of g. And this is just because if I compute the composition exactly in the way I just described, I'll get a circuit whose depth is this much. Now, in that paper, Karchmer-Wigderson conjectured that the depth complexity of the composition is roughly that, is roughly the sum of the depth complexities of f and g. In other words, this simple way of computing the composition is roughly the optimal way. And this is a very natural conjecture. It's very interesting in its own right, but they also noticed that if this conjecture was true, then that would imply that P is different than NC1. So this conjecture, if proved, would resolve this grand major frontier that we have in complexity theory. So we are very much interested in proving it. Now, some of you might be bothered by this approximate equality here, which makes the statement of the conjecture pretty vague. So I prefer to leave it vague because there are many variants of the conjecture that would imply P is different than NC1. So there is no real point in committing to one particular statement. But let's say that there are quite a few natural variants of that that would be good for us. Okay, so this is the conjecture. We really want to prove it. We don't know how to do it. Let's see what we do know. And in order to explain the known results, I first need to explain a framework called the Karchmer-Wigderson relations framework, which is the main framework we use to study this conjecture. And what this framework does is to relate the depth complexity of a function to the communication complexity of a related communication problem. This is the communication complexity techniques that Avi referred to earlier. Specifically, given a function f, we have this communication complexity problem, KWF, the Karchmer-Wigderson relation of f, or for short, the KW relation of f, which is defined as follows. Alice gets a string x on which f outputs 0. Bob gets a string y on which f outputs 1. And clearly those are two different strings, so they must differ on at least one coordinate. And the goal of Alice and Bob is to find at least one such coordinate on which Alice and Bob on which x and y differ. Now, the key observation of Karchmer and Wigderson was that the depth complexity of f equals exactly to the communication complexity of this communication problem. So this means that if we want to prove depth lower bounds on then instead we can prove communication complexity lower bounds on the Karchmer-Wigderson relation. And this is good because it gives us a different perspective on this problem. It allows us to draw on the tools of communication complexity. It's a very nice observation in general. Now, one technical detail I should mention is that when I'm talking about communication complexity throughout the whole talk, I only refer to deterministic communication complexity. Randomized protocols are a completely different story that is irrelevant to the KRW conjecture. So now that we have this framework, let's ask how does the KRW conjecture looks in this framework. And the way it looks like is saying that the communication complexity of the KRW relation of the composed function is roughly the sum of the communication complexities of the KW relations of f and g. Okay, now let's take a more detailed look on this phrasing of the conjecture. How does the KW relation of the composed function looks like? Well, remember that the composed function takes as input m by n matrices. So Alice and Bob now get m by n matrices, x and y, and their goal is to find an entry on which those two matrices differ. Now, what do they know about these matrices? Well, they know that if they compute G on every row of these matrices, then they would get two strings, A and B, such that if they compute F on those strings, they would get 0 and 1 respectively. This is the basic promise that they have, and they want to use it to find an entry on which the matrices differ. Now, taking this view, there is a natural way to solve this communication problem. So to see it, first note that A and B are a legal instance of the KW relation of F. So Alice and Bob can use the optimal strategy for the KW relation of F to find the coordinate on which A and B differ. Now, what does it mean that those coordinates of A and B differ? Well, it means that the corresponding rows of x and y have different value of G. That is, G outputs different values on these rows. So this means that these rows are a legal input of the KW relation of G. So now we can apply the optimal protocol for the KW relation of G and find the coordinate on which these two rows differ. And now we found an entry on which those two matrices differ. So this shows again that the communication complexity of the KW relation is at most the sum of the communication complexities. And the KRW conjecture can be viewed as saying that this obvious protocol is essentially the optimal protocol for this relation. Now, okay, obviously this is a hard question. So KRW also suggested a starting point, something that would allow us to get a handle on this question. And to that end, they defined what's called the universal relation. And the universal relation is a communication problem that is a simplification of KW relations. What it says is the following. Alice gets a string x, Bob gets a string y, and x and y can be any strings now. They don't need to be zeros or ones of some function. And the only guarantee is that x and y are different. And now Alice and Bob want to find a coordinate on which x and y differ. So this is some kind of a simplified version of KW relations that have no function involved, and it is quite well understood. It is not hard to prove that the communication complexity of this relation is at least n. And what KRW suggested is that we should try to prove the KRW conjecture for the composition of two universal relations first. Okay, so how do we even define this composition? Well, we define it in the following way. As before, Alice and Bob get two matrices, x and y, and their goal is to find an entry on which those two matrices differ. But now they cannot obtain the strings a and b by computing g on the rows because there is no function g. So instead we give a and b as additional inputs to Alice and Bob. And now Alice and Bob get two promises. First, a is different than b. Second, on every coordinate in which a and b differ, the corresponding rows of x and y also differ. Now, the point is that these two promises are all we need for the obvious protocol we had before to work here too. To see why? Know that since we know that a and b are different strings, it means that they are legal instances of the universal relation. So this means we can use an optimal protocol for the universal relation to find a place where they differ. And now, since due to the second promise, the corresponding rows of x and y are also different, so they are also a legal instance of the universal relation. And again, we can use an optimal protocol for the universal relation to find the coordinate on which they differ. So again, the obvious protocol works, and again, a natural version of the KRW conjecture would be that this optimal protocol is roughly optimal. And this challenge was met by Edmonds, Impaleazzo, Rudich, and Sgan in '91, who proved that this is indeed the case up to some small additive losses. And then an alternative proof was given by Hastad and Wigderson in '93. Now, going to the more recent past, to get in a joint work with Dima Gavinsky, Omri Weinstein, and Avi Wigderson, we also proved an analog of the KRW conjecture for the composition of a function and the universal relation, which is somewhere in the middle between the composition of two universal relations and the composition of two functions. Now, how do we define this composition? Well, just like in the composition of two universal relations, Alice and Bob get matrices x and y and strings a and b, and they know that whenever a and b differ, the corresponding rows of x and y also differ. But now they are also given the promise that f outputs 0 on a and 1 on b. So they can now so now a and b are actually legal instances of the KW relation of f. And again, it can be shown that the same obvious protocol from before works, and the obvious KRW conjecture would be that this obvious protocol is optimal, and we showed something like that, again up to some additive losses. And in a more recent result, we managed to improve these quantitatively, those additive losses, and now they are very, very small. Okay, so now we know how to prove the KRW conjecture for the composition of a function and the universal relation. And obviously what we want to do is to replace this bottom universal relation with a function, with some function g. So in another recent work, together with Dinur, we proved the KRW conjecture when f is some arbitrary function and g is the parity function over n bits. Now, this was actually already known. This was implicit in the work of Hastad on the shrinkage exponent. But we gave an alternative proof that is more in line with the spirit of the works, of the other works on the KRW conjecture, uses the KW framework, and in general, we believe that it has better chances of generalizing to other functions compared to the original proof. Okay, so this is more or less what we know about the conjecture. So I would now like to describe one proof strategy that has been useful for proving some of these results, starting from the work of Edmondson, Pagliazzo, Rudich, and Sgal from '91. What we want to do when we try to prove variance of the KRW conjecture is to prove that the obvious protocol is roughly optimal. But why should we believe that it is roughly optimal in the first place? Why intuitively should it be true? Well, one intuition is that what Ellis and Bob are trying to do is to find some entry on which those matrices differ. And in a sense, this is almost the same as just solving the KW relation of G on some pair of rows. And in particular, if they want to do that, then they must find a row on which the values of G are different on the row of X and the row of Y. If they can find such a row, then basically they don't have any handle on the row they are working on. They don't know, they are not using the promise they were given. So it makes sense that if they have any chance of solving this quickly, they must find a row such that the values of G on this pair of rows is different. And saying that the values of G on those rows is different is just like saying that the corresponding values of A and B are different, because the values of A and B are just the values of G on those rows. Now, the thing is that finding a coordinate on which the corresponding rows, the values of G is different, that is A and B are different, is exactly, by definition, solving the KW relation of F. This is what solving the KW relation of F means. So to sum up, they want to solve the KW relation of G on some pair of rows, and in order to know what pair of rows they want to work on, they have to solve first the KW relation of F. So this is basically saying that they have to run the obvious protocol. Now, this intuition is somewhat sketchy, but sometimes it can actually be turned into a proof. And indeed, sometimes we can implement this intuition using an adversary argument. And what does the adversary do? Well, the adversary is letting Ellis and Bob talk and run, and while they are doing that, the adversary measures the progress they make on each pair of rows in solving the KW relation of G. Now, whenever the adversary sees that Ellis and Bob have made too much progress on some pair of rows, the adversary just kills the row and makes their progress be for nothing. And the way the adversary does that is by forcing the equality AI equals BI. That is, it forces G to output the same value on this pair of rows. And we can show that if the adversary does it, then this prevents Ellis and Bob from solving the KW relation on this pair of rows. Now, the thing is that the adversary can keep doing that as long as they didn't solve the KW relation of F. Because as long as they didn't solve the KW relation of F, they don't know any coordinate on which A and B must be different, so the adversary has a free hand in forcing coordinates of A and B to be equal. And since the adversary can do that, the players have no choice but first solving F and then solve G. That's more or less the only thing they can do. Now, this is a very simplistic description. It's not so easy. There are lots of technical issues that need to be overcome, but sometimes they can be overcome. However, one specific issue I want to discuss now is I said that we are going to measure how much progress the adversary is making on each pair of rows towards solving the KW relation of G. How do we measure that? How do we measure that progress? So I don't know of any general solution, but here is a solution that sometimes works. Let's say that G satisfies some nice assumptions that will allow us to work with it. In particular, let's say that when we look at the KW relation of G on its own, now separately from the KW relation of the composed function, forget about the composed function for a moment. Then this relation has a lower bound proof that is proved using an adversary argument. Again, a separate adversary argument from the adversary argument that we just discussed. The KW relation of G has its own adversary argument. And moreover, let's assume that this adversary argument that proves the lower bound for the KW relation of G has some nice measure of progress that measures how much information, that measures how much progress the players made on this pair of rows. On the instances for KWG. And typically, this measure of progress will be indeed the amount of information that the players transmitted on their inputs or on some important aspect of parts of their inputs. So if we have such a nice adversary, then we can use this nice progress measure that the adversary uses back into the bigger adversary for the composed function. The adversary described in the next slide. So that's a very rough intuition of what we are doing. Now again, this is very sketchy and I don't have precise definitions for what a nice measure is and so on. But the thing is that this is basically the outline of what is going on in the proofs for the universal relation and the parity relation, KW relation. We have some nice information theoretic measure of what the players are doing, and we embed it into the adversary that proves the lower bound for the composed function. Now, for future reference, I would like to refer to this type of adversaries, information theoretic adversaries, because in all the examples I know, these kind of adversaries measure the progress of the players using some kind of an information theoretic measure. And this brings us to the discussion of where do we go next from here. So in order to prove the KRW conjecture, we now need to prove the conjecture for any composition of two functions f and g for arbitrary choices of f and g. Now, our previous works show that we more or less know how to deal with an arbitrary choice of the function f. I'm not so worried about this aspect. However, when trying to go on further and prove the conjecture, one sees that actually dealing with this arbitrary function g is much harder. And we don't even know how to prove the reverse version of what we know of a universal relation composed with g. And one reason for that is that an arbitrary function g may not have an information theoretic adversary. And even if it has, we don't know how to find it. So, I mean, it's not clear how to get past this obstacle. But now let's suppose that we don't want to prove the full KRW conjecture, but instead we only want to prove better lower bounds. So we just want to prove that P is different than NC1. Then there is some hope that maybe we don't need to deal with an arbitrary function g. Maybe we can find some kind of a complete function or some complete communication problem, such that if we deal just with this communication problem, then we will be able, then this will already separate P from NC1. And if we have such a problem, we will be very happy. We won't need to deal with an arbitrary function g. And if it also, this communication problem also have an information theoretic adversary, we will be even happier. And we have a candidate for such a communication problem, which is called the multiplexor relation. So I will now describe this candidate. So the multiplexor relation is basically the KW relation of a function g, except that now g is not a fixed arbitrary function, but rather it is part of the input now. So more specifically, the communication problem is defined as follows. Alice gets as an input a function g from n bits to 1 bit, and some string x on which g outputs 0. Bob gets the same function g and some string on which this g outputs 1. And now their goal is to find a coordinate on which x is different than y. Okay, so this is a very natural problem, communication problem. It is also in a sense a simplification of KW relations, and maybe you can also see why we think it should be complete. basically it is like the KW relation of the address function or the index function, except that we give the players this promise that they have the same function g here, which is not the case in the usual KW relation of the address function. Now, we understand this multiplexor relation relatively well, and in particular we know how to prove that its communication complexity is linear. So we don't worry about that. So now that we have this multiplexor relation, let's see how we define the composition. So in the composition of a function with the multiplexor relation, Alice and Bob again, as usual, get two matrices x and y, but now they are also given these m functions for each row, g1, g2 to gm, and now they obtain the strings a and b by computing every function g on the corresponding row. And again, they get the same functions. It's important that they get the same functions, g1 to gm. And again, the promise is that f outputs 0 on A and 1 on B. A natural analog for the KRW conjecture for that composition would be that the obvious protocol is optimal, which means that the communication complexity of this relation is basically the communication complexity of f plus omega of n. Now, this is a very interesting conjecture in its own right. For start, it is implied by the KRW conjecture. So if we are to prove the KRW conjecture, we should be able, for start, to prove this conjecture. But moreover, we have some evidence that suggests that if this conjecture is true, then this would actually already imply that P is different than NC1. We don't know it for sure, but it seems very likely. Okay, so this sounds like a good conjecture to go for. And in fact, I would like to mention that maybe even for start, it would be interesting to look at the composition of the universal relation with multiplexor, in which we are not guaranteed that some function f outputs 0 on A and 1 on B, but just that A and B are different. And then we have a very nice and clean communication problem that has no arbitrary functions involved. So maybe we can prove a lower bound on that. Now, another very nice property of this multiplexor relation is that it does have an information theoretic adversary. So this gives hope that maybe we have a plan for separating P from NC1. We first incorporate this information theoretic adversary inside the proof strategy that I described in the previous part. And we use this proof strategy to prove the KRW conjecture for the composition I just described in the previous slide. And then we use this proof to separate P from NC1. Now, this is a nice plan. Personally, I think it is a good plan. We should try to carry it out, but obviously I don't know how to carry it out. If I did, I would give a different talk today. Why can't we carry it out, or why is it not easy? Well, basically it's because the adversary of the multiplexor relation is very complicated and also very unrobust. Very simple changes makes it go wrong. And then, and this makes it very hard to incorporate this adversary in the proof strategy I described before. So I don't really know how to do that. So where can we go from here? Well, my feeling is that the good direction to go from here is to try to develop our techniques and extend them further such that they can handle more and more sophisticated information theoretic adversaries until they are finally strong enough to deal with the information theoretic adversary of the multiplexor relation. Now, how can we develop our techniques further? Well, my suggestion is that we first try to prove composition results by implementing that proof strategy I described with information theoretic adversaries that are easier than the one of the multiplexor relation, simpler than the one of the multiplexor relation, but still are more interesting than the composition results we know for the universal relation and the parity relation. And there are several nice communication problems with such information theoretic adversaries, so I suggest we try to prove composition results for them. So here are some candidates I have in mind. The Grigny-Sipser fork relation, the monotone ST connectivity relation, the monotone click relation. I won't have time to describe them, but they are very simple problems that have very nice and clean adversaries that you can find in textbooks such as the textbook of Yukna or of Kushilevich-Nissan. So can we prove composition results for those relations? Or maybe even just composition results with the universal relation? I think these are very good, nice and clean and hopefully tractable open problems that we can work on. So let me wrap up. So the KRW conjecture is a promising approach for proving that P is different than NC1. We know how to prove it when the inner function is the universal relation or the parity KW relation. And a possible approach to go further is to prove it when the inner function is the multiplexor relation. And some concrete open problems that I think are good would be to prove the KRW conjecture when the inner function is the fork relation, the ST connectivity relation, or the click relation. Thank you very much.
Well, Kaveh sets up. Are there any questions for Or?
Yeah.
How about when both we look at the monotone KW relation? Do we have any more composition down for those?
So that's another great question too. We don't even know how to prove the KRW conjecture in the monotone case. No, not in general. We know how to do it for very specific functions, which is what KRW did in the original paper, but we don't have any general proof of the KRW conjecture for monotone functions. Yeah.
Just a comment. You probably want to say why it's a good approach to proving P is different than NC1 despite the natural proof barrier.
Oh, thanks. Yeah, so the natural proofs barrier does not apply to this approach because this approach only proves a lower bound for a very specific function, so it does not have the largeness property of the natural proofs barrier. Thanks.
So,
Yeah.
So maybe, how does it work? The proof that P is different from NC1 from the.
Basically, what you say is that okay, you start from a random function over log n bits. So this has that complexity about log n, and it's explicit because it can be described using n bits. I'm sweeping some things over the rack, but basically it's explicit. And then you compose it with itself log n times, and you get that log squared n over.
So let's think Or again.